third day of myself transacting the lesson, that is chapter 11 P block elements, and today is 8th of November 2021. It is a Monday. Now, as discussed in the previous class, I was talking about this boric acid properties. Okay, so here and we also discussed about uses of borax. Okay, now today we'll be learning about orthoboric acid, which is commonly called boric acid. The formula is H3BO3 or BOH thrice. Now over here, please remember the trivial name of orthoboric acid is boric acid. The trivial name, the common name. It possesses the formula H3BO3 or BOS thrice. It is important compound of boron and it possesses medicinal values. Now preparation is required and only action of it, nothing more than that. Now preparation of this orthoboric acid is required from borax. Now I've already told you what is the formula of borax. Borax is Na2B4O7. So now when borax, that is Na2B4O7, it is reacted with sulfuric acid, then we get to see what you call the acid which is called boric acid or orthoboric acid. So I request you to learn this equation. Equations are more important in this chapter. The other method, that is from colemanite, you can leave this out. Only one method of preparation of what you call this boric acid from borax, that is only required. Now
Excuse me,
after that,
sir.
yes.
Sir, are you sharing the screen?
Uh, is it not shared? Just check.
No, sir,
No,
it's not
sir.
visible.
Oh, have you not opened your textbooks?
So it's not shared.
Have you not opened your textbooks?
Yes,
Okay,
sir.
never mind. I'll share it now. Can you see the screen now? Yeah,
Yes,
okay,
sir.
okay. Can you see? Just check.
Yes, sir.
Oh, because I thought you all are using your textbooks. Your textbooks, if you look at your textbooks, the new textbooks, it's on page number 649. It's on page number 649. Okay, okay. Now I think you can see. So I was talking about this orthoboric acid or S3BO3 or BOS thrice. Okay. Now this preparation only is required from borax. Only this part is required. Okay. This part. The equation is more important. And the preparation of orthoboric acid from colemanite, you leave it out. And as we know, after the preparation, we need to remember only the action of heat on boric acid. Only this property, number 4, only this one. Action of heat. Now, if you heat orthoboric acid above 370 Kelvin, there is a partial removal of water. It takes place. Water is removed, and we get metaboric acid. HBO twice, which upon further heating, it forms into an anhydride, boric anhydride. So this boric oxide is commonly known as boric anhydride is obtained. So I request you to learn this equation. Action of heat on what? Action of heat on boric acid or orthoboric acid. Only this much. Okay. After that, we'll move further. The uses are not mentioned in the syllabus, so we'll not waste our time for the uses. Structure of orthoboric acid. You can just have a look at the structure of boric acid. Two molecules of boric acid are linked to each other by means of some bonding. You can see over there. There is a bonding which is called hydrogen bonds. Okay. So this is the structure of boric acid, which will never be asked, but just have a look for illustration purpose only. Then come down to aluminium. On the same page, aluminium. Now this aluminium is required. Preparation of aluminium is required, and then reaction with acids and alkalis is required. Okay, so here aluminium, it was the first isolated by Waller in 1827, and remember this metallic element, aluminium, it is the third most abundant element in the Earth's crust. Since its atomic number is 13, the electronic configuration is of this type, the valence shell 3s2 3p1 over here. And we know, since it has 3 electrons in its valence shell, it can form tripositive ions. It is less electropositive than sodium and magnesium, however. Okay. Now, based on this, we'll be learning, try to learn about its reactions with acids and alkalis after this. Now, occurrence. With regard to occurrence, remember, it occurs as its ore, important ore, which is called bauxite, Al2O3 dot twice H2O. So remember the ore of aluminium, the important ore of aluminum, that is called bauxite. After that, properties. In the properties, we will go through only some important ones like reaction with acids and alkalis, which is there in the syllabus. So reaction with acid over here, number 3, under chemical properties. This is not required. Action of water is not required, but action of acid is required. So aluminium dissolves in dilute hydrochloric acid, forming aluminium chloride with the evolution of a gas which is called hydrogen gas. That is very important. Remember, action of acids. Okay, so it is reacting with dilute hydrochloric acid. Okay, so that reaction, you please learn this. Okay, then after that, reaction with alkalis. We'll have to go through the reaction with alkalis also. So with alkalis over here, you can see there is a similar reaction with acids. This also you can go through. It is forming aluminum sulfate, but here the acid, sulfuric acid used is hot and concentrated. Okay, then the reaction happens to produce sulfur dioxide gas. After that, number C, nitric acid, whether dilute or concentrated, has practically no action on aluminum. Nitric acid renders, it is an oxidizing acid, nitric acid. It renders it passive. It forms a coating of an oxide on the metal aluminum, after which the reaction does not happen. So that's why, remember over here, the reaction of aluminum metal with nitric acid makes it passive, unreactive for the reaction by the acid. Okay, so this is the reaction with acids, action of acids. Moving further, action of alkalis. Aluminum dissolves in caustic alkalis like caustic soda. Okay, it is reacting with sodium hydroxide, okay, to form sodium tetrahydroxoaluminate. It is sodium tetrahydroxoaluminate. Try practicing and learning this formula, sodium tetrahydroxoaluminate. Okay, that is the formula of the compound over here. It is a complex. Okay, so with the liberation of hydrogen gas, there is liberation of hydrogen gas. Okay, so only this alkali is important. Okay, now others not required. Action of metals not required. This is not also not required. Reducing action is also not required. Uses of aluminium. If you look at the uses of aluminium, it is, there are some important uses are there. It is used for making electrical transmission cables because of its strength. Okay, then due to its low density and good thermal and electrical conductivity and resistance to corrosion, it is used for making several alloys which are extensively used in automobile and aircraft industries. Okay, so that is sufficient for here. Then after that, you may just have a look at table 11.4 for illustration purpose, the various different alloys of aluminum, though it is not mentioned in the syllabus. This is something which I've learned in class 10 already. Okay, so just have a look at it. Magnesium, aluminum, magnesium, duraluminum, aluminum, there is magnesium, manganese and copper. Aluminum, bronze is aluminum, copper and tin. Okay, then gamma alloy, aluminum, copper, magnesium, nickel. It's a very good property over here for making aeroplane parts, gamma alloy. And there is nickel alloy for making airships. If you look at this aluminum nickel alloy, aluminum, copper and nickel. Okay, so these are some important alloys of aluminum. Now after this, what is required in a syllabus in detail is alums, different types of alums, their preparation and uses only. Okay, so here earlier, if you look at the alums, earlier the term alum was used to describe the double salt potash alum having the formula K2SO4 dot Al2SO4 thrice dot 24H2O. Okay, nowadays the term used is alum is used in a wider sense, and it is defined as alums are isomorphous double sulfates, iso potassium aluminum, isomorphous double sulfates having general formula. Now, what is the meaning of isomorphous? These two salts which are combined over there, like in, if you look at the formula K2SO4 dot Al2SO4 3.24H2O. Now these two salts, they have similar crystalline properties. They have similar crystalline properties, okay, because of the similar lattice energy. So that's why they are mentioned as isomorphous double sulfates. This both of these are sulfate, potassium sulfate and aluminum sulfate. So these two salts, when they are combined to each other, when they are linked to each other by means of a very weak chemical combination in the presence of water of crystallization, they give rise to alums. So this is how we define alums. Alums are isomorphous double sulfates having general formula given over there. M2SO4 dot M2-SO4 thrice dot 25H2O, where M stands for monovalent cation. This one is monovalent cation, okay, and this one is trivalent plus 3. Whereas M plus the dash stands for a trivalent cation such as aluminium or chromium or iron, ferric. So some examples you should remember: potassium aluminum sulfate, potassium chromium sulfate, ferrous ammonium sulfate, ammonium aluminum sulfate, and sodium aluminum sulfate. So remember, an isomorphous double salt, the cations present, one is monovalent, another one is trivalent, plus 1, plus 3. That is the meaning over here. Now, all these alums are isomorphous crystalline solids and they are definitely soluble in water. Their aqueous solutions are of acidic nature. So please remember this. The aqueous solutions of these double salts which you are going through learning them, they are what? Acidic, they are soluble in water. They are acidic in nature because of hydrolysis. Potash alum, it's a very common alum. It's preparation of one of them, we'll do it, okay, in detail, because that will be sufficient. The other methods also similar over here. Now to prepare potash alum, the first one is potash alum, that is potassium aluminum sulfate. Now to prepare potash alum, it is generally prepared from the mineral alunite or alum stone. Alum stone. This is the formula. Potassium sulfate, aluminum sulfate with 4 molecules of aluminum hydroxide. Now this mineral, which is alum stone, it is boiled with dilute sulfuric acid. See, it is boiled with dilute sulfuric acid and then it is filtered. It is filtered properly. The filtrate is mixed with a calculated amount of potassium sulfate. Again, the resulting solution is concentrated by means of boiling, okay, by warming it and then cooling it when crystals of potash alum are generated. So whatever resultant these two, this potassium sulfate and aluminum sulfate, the resulting mixture, it is some more quantity of potassium sulfate is added and then it is concentrated and then we get upon crystallization the salt which is called potash alum. So try to remember these equations, these two set of equations for the preparation of potassium aluminum sulfate from mineral alunite or alum stone, and learn the formula of alum stone. That's important, okay. Then the other method, it is from bauxite. You can see potash alum can also be obtained from the mineral bauxite, Al2O3 dot twice H2O. Bauxite is dissolved in sulfuric acid, okay, and bauxite is dissolved. After that, the solution is filtered and the filtrate is mixed with the calculated amount of potassium sulfate. The resulting solution on crystallization gives crystals of potassium. So the main thing is that it's a similar process. It is a very similar process. Now, properties of what you call alums are not mentioned in the syllabus. We will not go through them at all. Okay, but we will definitely what you call go through the uses which is there in the syllabus. Now here the uses of alum given over here. Number one, it is used as a mordant in dyeing and calcico printing. Mordant means what? Mordant is a substance which helps to fasten the color on any material. So if we add alum, if you buy a new cloth, if you buy a new shirt or a new pant which is colorful, okay, so when you wash it for the first time, if you take little bit few drops, few particles of alum and put it in the water and make a solution after adding washing powder and wash your colorful clothes, the color will not fade away. The color will not fade away. So in that way, I am using an alum as a mordant to fasten the color of the colored materials which I am going to clean by washing. Okay, so it is used as a mordant in dyeing and calcico-printing methods. Then it is used in tanning of leather. It is used for purification of water. We know we put lot of alum powder in the water tanks on the terrace of our buildings, okay, to purify water. It is used to stop bleeding also after shave, after shaving, when you use a razor blade to shave yourselves, shave your beard and the mustache over there, then by mistake sometimes because of some pimples arising on your face, there might be some small cut. So if you want to stop the bleeding, then you can wet some alum, okay, some small piece of alum, crystalline shaped alum, and then just rub it on the affected part. Okay, the bleeding stops immediately. So it is used as an alum. That is because of some ionic reaction happening over there. Okay, now this brings us to the end of the group 13 elements. After that, we are moving further to group 14 elements, which is called the carbon family. Now, in the group 14 elements, remember, we'll be going through the general characteristics, their electronic configuration, the occurrence, variation of properties, oxidation states, their chemical reactivity trends, anomalous behavior of the first element, that is carbon over here. So here, I'll just tell you over that the group 14 elements of the periodic table consist of like elements like carbon, silicon, germanium, tin, lead. These elements belong to P block of the periodic table and are called representative elements because their electronic configuration is very true to their group. Silicon is the second most abundant element, first being oxygen in the crust of the earth. Now, on moving from group 13 to group 14, the divergence in the chemical behavior between the first and the remaining elements of the group becomes more pronounced, and there is a steady increase in the metallic character on moving down the group. So if you're moving from carbon, silicon, germanium, tin and lead, if you move down this way, there is a pronounced increase in the metallic character, because we know carbon is a non-metal, silicon is a metalloid, it is a metalloid. Then this also we can talk about it's having metalloid properties, but this one is a metal. Lead is also a metal. So if you're moving from top to bottom in a group like this, the carbon family group 14, then from top to bottom the metallic character is more pronounced. The remaining elements of the group become more and more metallic in nature. Now, please remember that over here, carbon is strictly non-metallic. Silicon is essentially a non-metal and its chemical reactivity. Germanium is a semi-metal with pronounced metallic properties, and tin and lead are truly metallic in nature. Okay, so this was the introduction to the carbon family group 14 elements. Coming to the occurrence and uses over here for this group 14 elements, carbon is quite abundant in nature. In the native state, it occurs in the form of coal, charcoal, okay, bone charcoal, okay, wood charcoal, graphite, and diamond. In the combined state, it occurs as hydrocarbons, compounds of carbon, hydrogen, carbohydrates, carbonates, carbon dioxide, etc. It is an essential constituent of all living creatures and plants. Now, after that, silicon is the second most abundant element, 27.2% availability by weight in the crust of the earth. Now, this silicon, it occurs in the form of silica, sand, and silicates. Germanium is a trace element. We find it in very less amount in the crust of the earth, 1.5 parts per million. That means you will find only 1.5 grams of million grams of germanium in 1 million grams of the earth's crust. Okay, 1.5 ppm means what? 1.5 ppm means you will find 1.5 grams of germanium in 1 million grams of earth's crust. So that you have to remember this ppm concept I had explained in you in the chapter, the first chapter, that is some basic concept of chemistry. After that, now here coming down to these general characteristics of over here group 14 elements, moving to the electronic configuration straight away. Have a look at this chart. You should be able to write down the electronic configuration in the elaborated method as well as the brief representation as well, both the methods, because if you know the atomic number of carbon, you can easily write down the electronic configuration. Silicon is 14, so here is the electronic configuration. Germanium is 32 electronic configuration. Tin is 50 electronic configuration. and lead is 82 electronic configuration. Now here, watch very carefully. In germanium, there is introduction of the d orbital. In tin, there is introduction of the d orbital. Okay. In lead, there is a d orbital, there is f orbital. All. Okay. So as you move down in the group, there is introduction of the d orbitals as well as the f orbitals below. Okay. So that was the electronic configuration of the elements of group 13. Then coming down, have a look at this chart. This is the physical properties of group 14 elements. So this chart, you can just have a look at it for illustrative purpose only. Okay, not for learning the figures over here. Now, coming to some important physical properties of group 14 elements which are discussed below, atomic and ionic radii. Of course, the atomic and ionic radii of group 14 elements are smaller than those of the corresponding elements of group 13. That is true. So if you move from group 13 to group 14, if you look at the atomic and ionic radii, it becomes smaller in the case of group 14. The atomic and ionic radii increases on moving down the group. Reason is given over here. What is happening? On moving from group 13 to 14, what is happening? The effective nuclear charge is increasing. Therefore, the atomic and ionic radii decreases due to the stronger forces of attraction experienced by the electrons present in the outermost shells or the valence shell. So that is the reasoning given for the variation in atomic and ionic radii on moving from group 13 to 14. But if you're moving from top to bottom in the group, in the same group, that group 14, the atomic and ionic radii, they tend to increase because of the increase in the principal quantum number or the number of shells. The next one is density. Density over here. The densities of group 14 elements increase in moving from carbon to lead. The increase is slow in going from carbon to silicon, but becomes rapid on further moving down the group. This is how? This is because due to more effective packing of the constant particles in the high elements. Okay. Then coming to melting and boiling points, the melting and boiling points of group 14 elements show the following trends. Number A, the melting and boiling points of carbon and silicon are much higher than those of the other elements of the group. Reasoning is given over here. Carbon and silicon possess three-dimensional network, covalent bonded structure. This is why they have strong interatomic forces of attraction. Because of the strong interatomic force of attraction between the constant particles, and consequently have much higher melting and boiling points as compared to other elements of the same group. But if you look at number B, on moving down the group further, melting and boiling points decrease regularly because of the increase in the size. The atomic and ionic size becomes more. Now here, on moving down the group, the size of the atom increases due to addition of an electron shell in each element. This decreases the interatomic force of attraction between the constituent particles of the atoms. As a result, the melting and boiling point decreases. Then, looking at the ionization enthalpy of these 14 elements, the ionization enthalpy values of these elements follow the following trends. The first ionization enthalpy of group 14 elements are higher, definitely, than those of the corresponding elements of the group 13. Explanation: this is due to the effective nuclear charge becoming higher and size becoming smaller. Then number B, the ionization enthalpy decrease on moving down the group because of increasing atomic size. Okay. The number C, the decrease in the first ionization enthalpy values is very sharp from carbon to silicon, followed by a slower decrease up to tin. The ionization enthalpy of lead is slightly higher than that of tin. Reasoning is given over here. The reasoning is because of two things over here. The poor shielding effect. Have a look at that poor shielding effect of d electrons. D electrons are not able to shield the effect of the nucleus on the valence electron. Because of that, the lead is slightly higher. The IP of lead is slightly higher than that of the tin. The next one is the increase in the size of atoms on moving down the groups. If you're moving down the group, the size of the atom is increasing. That's how the ionization enthalpy of lead, if you compare with tin, it is slightly higher. Okay. Then coming to electronegativity. The group 14 elements have higher values of electronegativity than those of the corresponding elements of group 13. The electronegativity decreases in going from carbon to silicon and then assumes almost constant value for the remaining elements. Okay, let us slightly higher electronegativity than that of tin. Explanation: The higher electronegativity of these elements as compared to those of 13 elements may be attributed to the smaller size of the atoms. The size is smaller, so electronegativity is higher. So, smaller the size of an atom, more is its tendency to pull electrons. That means more is its tendency to become electronegative. Okay. Now, after that, electropositivity, that is metallic character. The group 14 elements are less electropositive and hence less metallic than the elements of group 13. If you look at over here, carbon and silicon, they are two non-metals. Germanium, it's metalloid, and tin and lead are metals. Explanation: the less electropositive character of group 14 elements is due to the smaller atomic size and higher ionization energies as compared to those of group 13 elements. Okay. On moving down the group, the size of atom increases and ionization energy decreases. This is why electropositive character and hence the metallic character increases on moving from carbon to lead. Okay. Then allotropy. I hope you remember the meaning of allotropy: existence of an element in more than one form. For example, if you talk about carbon, all the elements of group 14 except lead show allotropy and exist in different allotropic forms. Carbon has two well-defined crystalline form, diamond and graphite allotropes. So please remember this. They exist as diamond and graphite. Besides this, carbon also exists in several microcrystalline forms such as coke, charcoal, carbon black, etc. etc. Silicon is known to exist in both crystalline as well as amorphous forms. Okay. Germanium exists in two crystalline forms. Tin is known to exist in three forms: gray tin, white tin, and rhombic tin. But lead will not exhibit allotropy. So the element from group 14 which does not show allotropy is lead. That could be a question. Okay. This does not exhibit allotropy. Allotropy. Okay. Then coming to the next important, very, very important property of the elements of this group, that is called catenation. Now we know the meaning of catenation. It's the ability of an element to form long chains or rings by linking its atoms with one another through covalent bonds. Okay. Among all these elements of group 14, the tendency of catenation is higher with carbon. Carbon forms a large number of compounds in which a number of carbon atoms are linked to each other through covalent bonds, either in chains or in the form of rings. So, on moving down the group, the catenation tendency will decrease. The variation is given over here. Variation of catenation property is given. Explanation: the tendency of catenation depends upon the strength of this element MM bond, where M represents an atom of the given element. The strength of the MM bond is in turn depends upon its bond energy. Higher the bond energy of MM bond, more its strength and greater is the tendency. Okay. Then after that, number 9, oxidation states. Oxidation states. Now, this oxidation states is so important that without the knowledge of oxidation states and nature of compounds of these elements, we will not be able to get an idea about the chemical reactivity of the elements of this group. So, it is important to understand the oxidation states and the nature of the compounds formed by these elements. Okay, so here the common oxidation states, remember, of the group 14 elements are +4, first one, and +2. On moving down the group, the stability of +4 decreases, while +2 oxidation states become more and more stable. This is because of inert pair effect. We can talk about that. Okay. So this is because of what? Inert pair effect. So remember this paragraph more importantly. This paragraph more importantly. Okay. Now, moving further to this carbon, the last paragraph, carbon and silicon show great tendency to form covalent compounds with the exhibit tetravalency. The tetravalency of carbon and silicon can be explained below over here. Have a look at this. Carbon in the ground state. In the ground state, it has 1s 2 electrons, 2s 2 electrons, 2p 2 electrons in the 2px and 2py orbital. But in the excited state, 1s 2 electrons are there, 2s 1 electron, and 2p 3 electrons are there, 2px, 2py, 2pz. So it is showing tetravalency. Because of its tetravalent nature, it is more capable. It is more capable of showing, exhibiting what you call the property of what you call catenation. Okay, that will be sufficient from here. Okay, then tendency to form multiple bonds Again, it depends upon this tetravalency. The elements of group 14 can enter into the formation of multiple bonds through p pi p pi and d pi p pi bonding. So it is forming pi bonds by using its p orbitals. So that is forming p pi p pi by the sideways overlap, and d pi p pi, that is by the overlap of the d orbitals and the p orbitals sideways overlap. Okay, it is possible. So that is sufficient for this. Rest you leave it out. Then coming to the chemical reactivity, of group 14 elements over here. Uh, Under this chemical reactivity of some group 14 elements here, just a second, I will just tell you what is required. Uh, yeah, over here, the tetrachloride of carbon, that is carbon tetrachloride, is not hydrolyzed by water. So there is no reaction. Just try to learn this equation. Whereas silicon tetrachloride reacts with water to form silicic acid. Only this is required. Okay. After that, moving further, this is not required. Nothing is required from here. Then silicon crystal structure of silica. Have a look at this. That is the crystal structure of silica. Okay. Then nature of dioxides. You try to remember. Carbon dioxide, silicon dioxide, acidic. Germanium oxide, it is weakly acidic and weakly basic. Whereas tin oxide and lead dioxide, it is amphoteric. Okay. This can be proved from these reactions. Then coming down, anomalous behavior of carbon. That is important. Anomalous behavior. Why is carbon behaving in an anomalous manner? Carbon, being the first element of the group, differs from the other elements in its own group in several properties, which can be seen over here pointwise. It has been explained. Okay. The first reason is carbon, its atomic size is small. Its electronegativity is higher. The absence of vacant d orbitals in its valence shell makes anomalous. It has got strong catenation tendency. Okay, so these are the main reasons why it shows anomalous behavior. Now, because of this anomalous behavior, the important properties of carbon differs from other elements of the group in this following manner. Because of this, carbon is much harder than the other elements of the group. Diamond alloy of carbon is the hardest substance known to us. The melting and boiling points of carbon are much higher as compared to those of other elements of the group. The tendency of catenation is maximum in the case of carbon because of its tetravalency. Number 4, carbon possesses a remarkable ability to form p-pi multiple bonds with itself and with other nonmetals such as nitrogen, oxygen, or sulfur. It can also form d-pi p-pi bonding, possibly with higher elements. The number 4, CCl4 does not undergo hydrolysis, whereas tetrachlorides of other elements they undergo. So the reaction I have already told you that time. Number 6, carbon dioxide is a gas at room temperature, while the dioxides of other elements are solids, networked solids. Carbon does not take part in a complex formation due to the absence of vacant d orbitals. So remember this important. Carbon does not take part in a complex formation. Carbon will not form complex compounds. Because of what? Because of the absence of vacant d orbital. But if you look at the other elements, silicon, germanium, tin, lead, they have a possibility of forming complexes. Okay. Then after that, we'll move down further. Over here, we'll not go to the allotropes of carbon. Allotropes of carbon will not go through this. Okay. This is not required. Structure. Structure of diamond and graphite and fullerene is required. Structure of diamond and graphite. Structure of diamond is here. So this structure of diamond is required. Look at the structure of diamond. Here it possesses a three-dimensional network of carbon atoms joined together through strong covalent bonds. Each carbon atom is in a state of sp3 hybridization and linked tetrahedrally to four neighboring carbon atoms. So this you learn properly. Okay. Properties are not mentioned in the syllabus. Okay. Here, remember, all carbon-carbon bonds are equal and equal to 154 picometer. And the bond angle which you see over there, the bond angles over here, carbon, it's roughly 109 degrees 28 minutes. Okay, that is sufficient from here. Then coming to the structure of graphite. The structure of graphite, that is also important, that is also required. Okay. Here in graphite, each carbon atom is in a state of sp2 hybridization and is covalently attached to three neighboring carbon atoms lying in the same plane. So this is one plane. This is one plane. There is another plane. Okay. Okay, and these two planes are held to each other by weak van der Waals forces and are separated by a distance of 340 picometer. So because of these weak van der Waals forces, the sheets are not firmly attached and can slide over one another. That's why graphite is used as a lubricant in machinery. Okay, that is sufficient. Then the structure of fullerene. If you look at the structure of fullerene over here, the structure of Buckminster fullerene, that is C60, the molecular shape has a shape like a soccer ball, soccer ball over here. Okay, that is only there. Now in fullerene, up to 60 carbon atoms. There are 60 carbon atoms in the ring. Okay, that is sufficient. Then with regard to the stability, I've already told you. Okay. Then chemical properties. Chemical properties. Here, go through the reactions. Burning of carbon. Reaction reaction with metals, calcium and aluminum, reaction with oxides, calcium oxide, silicon dioxide. Just go to the reaction, you should be able to write on the reactions. Okay. Carbon with hydrogen to form acetylene, sulfur, carbon disulfide, silicon with fluorine, with acids. These reactions you go through, you should write them down. Then reducing properties. Reducing properties, you go through them properly. Because the carbon is a reducing agent. It reduces metallic oxides like zinc oxide, iron oxide, lead oxide, barium sulfate, okay, to give the respective metals and liberate carbon monoxide gas, okay. When red hot carbon is reacted with steam, it produces carbon monoxide, okay, Bosch process, okay. So here, uh, we'll stop the class here only, okay. In the next class, hello, can you hear me? I'll be continuing with some important compounds of
Sir,
carbon from here. Okay. So it's already time up. The bell has already gone. So I'd like to stop my class here only. But please hang on because I need to record your attendance immediately. So in the next class, I will discuss about some important compounds of carbon and silicon. Okay. And proceed further to complete this chapter. Okay. So just hang on. So today I have only 32 students left over here. Okay, let me record the attendance first. Then we will leave the class. Okay. Okay, attendance is recorded. Thank you so much, boys. Have a nice day.
sir.